and begin chapter 4. So for, I'm just going to turn down the volume here, it's ringing a bit. In the second term, the main topic is to go through single variable calculus. Okay? So I'll be taking you through the theory of the derivative, okay, the concept of differentiation for real value functions, and Saeed will be taking you through the theory of the integral of functions of one variable. I'll also be giving some general material or some overarching material connecting the two concepts of differentiation and integration, because of course they're intimately linked. Then I've also got a second term topic on as an introduction to group theory, and that will occupy us for the last few weeks in term 2. So the differentiation material, so the main kind of topic for term 2 is here in chapter 4, but at the start there's some material on continuity of real valued functions. Okay, so that's the thing we're going to look at today, just as an introduction to these ideas, and then I might speak a little bit more about it in one of my lectures next week, and then when we come back in term 2 we'll get going with looking at the theory of the derivative. Okay. Now for these topics, just to remind you here of some good other resources to use outside of the notes, there's 3 main books I'm going to recommend. There's this Sham's Outline of Calculus book, Modern Engineering Mathematics by Glyn James, and similarly titled Engineering Mathematics by K.A. Stroud. And don't be put off by the term engineering mathematics in these. I mean, it's pretty standard calculus material that these books are describing. The engineering prefix just kind of indicates where a lot of their examples and applications are coming from. But the theory they go through is still very mathematical. Now, the situation has changed. In these descriptions here, I'm referring to the fact that the Sham's Outline of Calculus book is available as an ebook through the library website. This is now even better. Now, the Modern Engineering Mathematics book is available as an ebook there too. So if you look down the right-hand side of the unit's Moodle area, in the library block here on the right-hand side, under Essential and Further Reading here, you've got this Calculus, that's the Sham's Outline of Calculus book, and down here, Modern Engineering Mathematics, that's the Glyn James book. When you click through those links, you go through to the library website, and you click through further, you can access the online PDF copies of those books. Okay, so they're very, very accessible to you. And those books contain alternative explanations of the things we're going to talk about, lots and lots of exercises and examples and example problems for you to look at. So they're very good resources to use, and I'd encourage everybody to make use of those. Okay. Okay, so starting to talk about this in detail then, what we're going to be concerned with is studying the behavior of real valued functions. Okay? Functions defined on the real numbers and taking values in the real numbers. Okay? Now, when we looked at functions in chapter 3, we were very careful to say that part and parcel of the definition of a function is a precise description of what the domain of the function is and what the codomain is, a precise description of those sets. Now, in practice, we don't, when we want to introduce functions and talk about them, we don't always take the time to specify exactly what their domains and codomains are. But for the most part, it'll be clear from the context what the domains and codomains are. We're studying real value functions, so the domains and codomains are always subsets of the real numbers. And we'll normally take their domains and codomains to be the kind of maximum possible ones. So a little example here, so we might talk about the reciprocal function defined by the formula y equals 1 over x. So that's a function of x. Now, I can introduce it and talk about it. I won't explicitly say what the domain of that function is, all the time. But if it ever is an issue, what the domain of it, what range of possible arguments x you should be considering, well, unless we state otherwise, we should take the domain of this function to be the real numbers, but without 0, so the non-zero real numbers. You have to exclude 0, of course, because the function doesn't make any sense for the value x equals 0. You can't divide 1 by 0. Okay, so we won't always talk about domains and codomains. They can normally be understood when you consider the function, what's a reasonable domain for the function, and so on. Okay. Now, in calculus, in studying the derivative, so in a nutshell, what's the derivative of a function? The derivative of a function is a measure of how fast the function is changing at any moment. Okay. So it's also described as the instantaneous rate of change of a function. Okay. How is the function behaving at this moment in time? Is it increasing or decreasing, and so on? Or how is the function behaving at this element in its domain? Is it increasing at that value or decreasing, and so on? And if it is increasing, how fast is it increasing? If it is decreasing, how fast is it decreasing? So this studying a function at a single moment is going to involve the idea of considering the behavior of the function across an interval, and then shrinking that interval down to a single point, so that you capture the kind of instantaneous behavior of the function. So we can study the behavior of a function across an interval, but then as we want to shrink that interval down, this is going to be a limiting process. We're going to be studying quantities related to the function values defined across an interval, but then taking the limit of this expression as we shrink the size of the interval. So before we get on to talking about the derivative in detail, we want to introduce the notion of talking about the limiting values of a function. Now this is very much related to, or very similar concepts to where we looked at convergence in sequences and series. Okay? We're studying how something changes as we change a parameter, and then considering what the limiting behavior is as we continue to change the parameter. When we looked at sequences, we were increasing the index of the sequence and looking at how the terms of the sequence evolved and whether there was any limiting behavior there exhibited by the terms of the sequence. Here now we're not looking at, so sequences are just lists of numbers. Here we're looking at something more abstract or more complicated, a function, something which is defined for every real number x, not just defined for integer values, 1, 2, 3, and so on, which is what a sequence is. Okay. So we're going to be talking about things like this expression here, the limiting value of the quantity f of x as x tends to a. Okay? That's the kind of thing we're going to talk about. And if we write something like this, that the limit as x tends to a of f of x equals L, that's how I'm reading that first equation there, the limit of f of x as x tends to a. If we say that that's equal to L, what we mean is that as the argument x gets closer and closer to the value a, the values of the function f of x are getting closer and closer to the limiting value L. Okay. Now that's described in vague enough terms at the moment, but its correct description gets across the right idea. Other alternative notation for it is to say f of x arrow L as x arrow a, but of course you read that in English, if you're reading that on the page, that's saying f of x tends to L as x tends to a, or f of x converges to L as x converges to a. Okay. And one thing to notice early on is that this definition, it doesn't actually make an explicit reference to the value of the function at a. So this limiting behavior of f of x as x tends to a, it's actually independent of the value f of a. Okay. But we'll connect the two things shortly when we introduce continuity. So here's a quick visual example. We could consider this function here, or the function which is represented by this portion of a graph here. Now this is kind of displaying some complex behavior, because if you consider the limit of this function as x tends to 1, it's a bit ambiguous what it should be, because if you come at 1, if you converge to 1 from the left-hand side, from values less than 1, it has a limiting value of 2. Whereas if you converge to 1 from the right-hand side, from values greater than 1, we find the function has a limiting value of 4. And both of these are different to the actual value of the function at 1. F of 1 here is suggested that it's equal to 3 by the graph of the function. So we can build this kind of concept into our notation. And if we write here the limit as x tends to a with a superscript minus sign on the a, that indicates that you're approaching a from the left, from values less than a. The second expression there, the limit as x tends to a plus, that indicates that you're considering the limit as x tends to a from values greater than a. Okay. We can also expand the notation by bringing in the symbol infinity. Okay. We could write the limit as x tends to a of f of x equals infinity. Now we're not implying here that infinity is a number or that infinity is an element of the codomain or anything. This is simply a shorthand way of saying that the limiting value of f of x as x tends to a, well, that there is no limiting value. The values of f of x are getting larger and larger without any upper bound as x approaches a. An example of this is this function that we introduced a moment ago, this reciprocal function 1 over x. So we can say a couple of things about this. We can say the limit as x tends to 0 from the left, from values less than 0. That limit of the function 1 over x we can say is equal to minus infinity, because there the values are decreasing. They're getting larger and larger in the negative direction. And there's no upper bound to the absolute value that they can take as you get closer and closer to 0. Similarly, as you approach 0 from the right-hand side, the quantity 1 over x is going to plus infinity. Okay? There's no upper bound to it. We can also bring infinity into, use infinity as the value for, or to take the place of the quantity a in the limit notation. We could say that the limiting value as x approaches infinity of f of x equals L. That's to just say what the limiting value of f of x is as x gets larger and larger in the positive direction. Okay. Or similarly, the limit as x tends to minus infinity, as x gets larger and larger in the negative direction. And for the function 1 over x, these limiting values are both 0. And we can appreciate all of this from the graph of the reciprocal function. So this red graph here is the graph of the function 1 over x. And you can see, as you get closer and closer to 0 from the left, the values are getting larger and larger in the negative direction. As you approach 0 from the right, they're getting larger and larger in the positive direction. So that says the limit as x goes to 0 is either minus infinity or plus infinity, depending on which direction you approach x from. And the limit of 1 over x as x goes to plus infinity is going to be 0. The graph is curving down here towards 0, and if you extended the graph to the right there, you would get closer and closer to the value 0. It never does get to 0, of course, but its limiting behavior is described as converging to 0. And similarly, as x goes to minus infinity, out to the left here, 1 over x is also converging to 0. And remember, when we introduced limiting values for sequences, we then went through the theory of this concept, and we investigated properties of convergence itself. And we've got a very similar looking result for limiting values of functions. Indeed, we're going to refer to it by the same term, call it an algebra of limits theorem. And this tells you how this limiting process behaves and how it fits with the arithmetic operations that we can perform on functions. So in chapter 3, we talked about how we can consider functions as objects in their own right. For real valued functions, we can add them together. We can multiply functions together. We can divide one function by another one, as long as the one you're dividing by avoids 0. And all these operations on functions, they fit well with the limiting process. Okay? So we have a linearity result, the first one, which says the limit as x tends to a of a linear combination of functions, alpha times f plus beta times g. When you evaluate that at x and consider its limiting behavior, well, as long as the individual functions f and g have limiting values, then we can say that the limit of the linear combination of the two functions is equal to the linear combination of the limits. So alpha times L plus beta times M. Similar result for products. You're taking the limiting value of a product of two functions. Well, if the two factor functions have limiting values as x approaches that a, then the limiting behavior of the product will be to converge to the product of the limits. Yeah. So the limit as x approaches a of f of x times g of x is going to be L times m. And a similar result for quotients, providing we avoid 0, providing the function g of x is never equal to 0, and that the limit m that g of x approaches is not equal to 0 itself. Okay? Because it wouldn't make much sense to write L over 0. And there's another property of limiting values of functions which we're kind of introduced now, although it's kind of awkward because it relies on the derivative, and we've yet to go through the theory of the derivative. But you do all have exposure to the concept of the derivative already and know how to take the derivatives of some standard functions. So there is a result called L'Hopital's rule, and that can help you determine limits of quotients in situations where this quotient rule here in the algebra of limits theorem cannot be applied. So if you get situations where the functions f and g are both approaching 0 as x approaches a, or if they're both approaching infinity as x approaches a, you can't make use of the algebra of limits result. Okay? You can't consider a limit 0 over 0, because 0 over 0 does not make sense. Equally well, you can't consider a limit infinity over infinity, because infinity isn't a number. You can't go dividing things by infinity or divide infinity by something. Okay? So those expressions don't make sense. So the algebra of limits theorem does not apply, but what might apply, what might help you get the limit, is to apply L'Hopital's rule. Okay? And that says that, well, if the derivatives of the functions exist, and if they have limiting values, and if the limiting value of the quotient of the derivatives, that's on the right-hand side here, the limiting value of the quotient of the derivatives, if that limit exists, probably worked out using the algebra of limits theorem or some other method, then the two limits will agree. The limit of the quotient of functions f and g will be the same as the limit of the quotient of the derivatives. Okay. So we've got a bunch of examples here which display. Now we'll be returning to L'Hopital's rule. I just want to bring it in now and show you some applications of it, but we will be returning to it, and I will seek to justify it. Once we have the theory of the derivative at our disposal, I will seek to prove it and persuade you why it's true, give an argument for it. But in example 4.1 here, you can see a number of examples. Now, I haven't put in all the explanations, but you could go through them now, which show applications of either the algebra of limits result or of L'Hopital's rule. In the first example there, you're taking the limiting value as x goes to infinity of 3x plus 1 over 2x. Now, neither the numerator or the denominator do have limiting values there. They both are unbounded. They both approach plus infinity. So that might be a candidate for using L'Hopital's rule, although if you do some rewriting of the function, you can avoid using it, because you can do a move here similar to one that we used with sequences. So we can divide above and below by the quantity x here. So we're not changing the quotient, we're changing the way the quotient is represented. So now it's represented as 3 plus 1 over x divided by 2. And that, it is easy to see, or it is, we can apply the algebra limits theorem to that to work out its limiting behavior. Because the quantity, well, the 3 and the 2 are just fixed constants, and 1 over 6 converges to 0. Sorry, 1 over x converges to 0. So in the limit, as x tends to infinity, 3 plus 1 over x divided by 2 will converge to 3 over 2. The next example, the limit as x approaches 0 of sine of x over x. That's an important result which really should be proved from first principles by considering the geometry of the situation. But we're presenting it here as an application of L'Hopital's rule. So we can differentiate the top and the bottom. If we do that, then the denominator becomes 1 and the numerator becomes cosine of x. The cosine of x does have a straightforward limit as x approaches 0. Cosine of x approaches the value 1. And you got a constant 1 on the bottom, so you get the value 1 overall. Now that's a bit of a kind of a cheating example, because we're making use of the derivative of sine, but actually to prove that the derivative of sine is cosine, you have to actually use the fact that the limit as x approaches 0 of sine of x over x is equal to 1. So really, that result should be proved without appealing to the derivative, because it's a thing, it's a result you need in order to establish what the derivative of sine of x is. So maybe, I mean, at a later date, I really should, to be fair, show you the explanation of why the limit as x approaches 0 of sine of x over x is equal to 1. It should be proved from first principles, from the geometry of sine of x, from the definition of sine of x. Other examples there, the limit, example 3 is another example of the application of the algebra limits result. First, again, by dividing through by x. Example 4 is another example of L'Hopital's rule, where the derivative of sine of 2x is 2 times cosine of 2x. Gives you a limit of 2/3 then, as x approaches 0. And example 5, again, another one for L'Hopital's rule, this time using the derivative of the exponential function. And example 6 is a nice one. Example 6 is displaying a case where you have to apply numerous applications of L'Hopital's rule. Because the first limit, both the top and the bottom approach 0 as x approaches 0. Okay? Sine of x approaches 0, x approaches 0, x cubed, they all approach 0. So we got a 0 over 0 limit. So we can apply L'Hopital's rule. But when we do, we again have a 0 over 0 limit. And we apply L'Hopital's rule again, we again have a 0 over 0 limit. I mean, this process might go on forever and you never get to any conclusion. But because the denominator function is going to simplify to a constant, right, if we keep differentiating it, eventually we get single cosine over 6. So at this final stage now, this final equality here comes about from applying the algebra limits. Cosine x part is approaching 1 as x approaches 0, so minus it divided by 6 will approach minus root 6. Okay. Now, there's a number of examples in the end of chapter exercises, which are through on page 55, which you could consider in the tutorials this week, which ask you to apply these ideas. So, okay, any questions at this point, or any clarification? Any of that? Is okay? Okay then, so the next section is this concept called continuity. Now, I indicated beforehand that the limiting value of a function as x approaches a, say, it doesn't depend on the actual value of the function at the limiting argument. This example showed a function which has a certain value at 1, so f of 1 is equal to 3, and we could change it so that f of 1 equals any value at all. But the value that the function f has at 1, it doesn't affect the limiting behavior of the function. Okay? The limiting behavior of the function is only determined by what the function does at points close to 1. Close, or what it's doing as the argument gets closer and closer to 1. So it doesn't act, it's actually independent of the value or whether the function is defined at all at the limiting argument. But that's not to say that there shouldn't be a relationship between the two. Okay? So continuity is a property that functions might have. It's considered a nice property of functions. So functions that are continuous are well behaved in a certain sense. Being not continuous is kind of bad behavior or awkward behavior for a function in a way. And this is the definition which we're going to give more detailed forms of the definition. But a kind of short and sweet form of it is this here. So a function is continuous. Now it's continuous at a certain point in its domain. So we would say that f is continuous at the point x equals a if the limiting value that the function has as x approaches a, if that's actually equal to the value of the function at a itself. So if the limiting value of f of x as x approaches a is equal to f of a. So let me just switch to the overhead a bit. So continuity of functions can be represented by well, I hesitate to use the same word again, but by continuous or connected behavior of the graph of f. So, you know, here's the graph of a function f of x, and as long as I draw the graph of it without lifting my pen off the paper, I'm drawing it in a kind of smooth, continuous, connected way, then it's suggested that it's continuous. Okay, that's a continuous function. So here, I mean, here's a point A in its domain, and if you consider the limiting value as x approaches a of the function, well, if you approach a from either side, the values of the function will approach this point, which is of course equal to f of a. Okay? So this function is showing good continuous behavior at all points in its domain, or at least the points we've represented there. So non-continuous behavior, on the other hand, might, now I won't say it always looks like this, but it might look like this. Might look like the following, where you've got a function that's coming along nice continuously, but then suddenly it kind of, in an instant, it changes its behavior, and it makes an instantaneous, discontinuous change in value. Okay? Now, it isn't, say, represented there what the value. If we put a filled-in circle here, we're saying that the value of f at a is given by this lower value. But immediately, for any value greater than a, this is suggesting that suddenly the function takes much higher values. Okay, so this is discontinuous at a. Always have trouble spelling the word discontinuous. U-O-U-S. Discontinuous at x equals a. We might, however, describe this though as piecewise continuous. Okay, we won't worry about a very precise definition of that, but piecewise continuous means the function is made up of two continuous pieces. It fails to be continuous at this particular point, but if you look at it at other points in its domain, it seems to be continuous at every other point. Okay, but here's a point of discontinuity. Now, most of the standard functions we talk about, functions which have nice definitions given by nice formulas, they tend to be continuous. First, they have to be considered carefully, and you have to prove that they're continuous. But polynomial functions, for instance, are continuous. Most of the trigonometric functions, sine and cosine, they're continuous everywhere. They always change in a connected, continuous way. And points of discontinuity don't always fit into this kind of sudden change picture. So this picture is kind of showing a instantaneous or sudden change in value, which is taking place here. So there's another type of discontinuous behavior shown in that graph on page 37, which just put on the screen now. So this is the graph of the function sine of 1 over x. Now sine of x, of course, is a nice continuous function. You have this continuously changing smooth sine wave, okay, which just goes up and down as you go along the x-axis. Sine of x is continuous. But if you consider the function defined by sine of 1 over x, so this is the composition of sine with the reciprocal function, sine of 1 over x, it's continuous everywhere, but something funny is happening at 0. Well, for a start, the function, that formula doesn't make sense at x equals 0. Sine of 1 over 0 is not defined, so sine of 1 over 0 can't be defined. But even if we made a decision about what the value of this function should be at 0, no matter how we define it, it'll never be continuous at x equals 0. So if you think what happens as x gets close to 0, let's consider x getting closer and closer to 0 from the positive side. So x is getting smaller and smaller. Well, as x gets smaller and smaller, the argument to the sine function, the 1 over x, is getting larger and larger. So you're evaluating sine at a quantity which is growing without any upper bound. Now, if you think of the original sine function, if you grow x without any upper bound, sine of x continues to vary between +1 and -1. Nice, smooth behavior. But here, we're forcing it through all of that infinite amount of behavior. Sine of x, if you consider the argument of sine of x getting larger and larger, it goes up and down an infinite number of times. We're forcing it to display that infinite number of cycles in just this finite amount of space, in just the space between 1 and 0, say. Okay, so as x gets closer and closer to 0, the 1 over x gets larger and larger, and so sine of that quantity has to go up and down, up and down, up and down, faster and faster. And indeed, the resolution of this plot isn't huge, it's a bit blocky, but even if I had amazing resolution for this function here, it would still break down as you got closer and closer to 0. Because the function is trying to go through an infinite number of cycles in just this small space around 0. So what's the limiting value? What's the limiting value of sine of 1 over x as x gets close to 0? There is no limiting value. It doesn't have a limiting behavior because it's constantly moving up and down between +1 and -1. And it's doing so an infinite number of times as you move across 0. Okay? So there is no single limiting value of the function. So the upshot is that sine of 1 over x is not continuous at x equals 0, and there's no way to make it continuous at x equals 0. There's no possible value that you could assign to the function at x equals 0 which would fix it, which would make it continuous. So continuity is an important property of functions. And again, we've got a kind of theorems about how continuity itself behaves and how continuity, as we're carrying forward a similar theme, had this new concept of continuity, how that fits with the operations that we have on functions. So we can add together functions, we can multiply functions. Another important property is we can compose functions. So theorems 4.3 and 4.4 say that continuity fits well with all these operations. If we've got two functions that are continuous at a certain point, if you add them together or take any linear combination of the two functions, that again is continuous at the point. Similarly, if you multiply together the functions, you consider the product function, f times g, here in theorem 4.3, that will be continuous at x equals a. Similarly for quotients. And for compositions, when we run together, when we compose two continuous functions, the overall result, the composition of them, is again continuous. So this nice behavior, this nice continuous behavior of functions, it's preserved by composition. Now, we'll just finish by giving you a first look at the formal definition of continuity. Okay? Because when it comes to proving properties, general properties like those in theorems 4.3 and 4.4, general properties about the concept of continuity itself, the definition we've given up to now isn't detailed enough. Okay? So we need a formal definition of continuity. And it's kind of similar to the situation when we were looking at sequences. Our original informal explanation of convergence of sequences, we said it converges, sequence converges to a limit L if the sequence elements get closer and closer to L. Well, it was a bit vague, and there was too much going on or too much hidden in that closer and closer to phrase. So the formal definition of continuity for sequences was that epsilon capital N definition, which attached parameters to how fast the sequence was converging, and whereabouts in the sequence it was getting closer to the limit. Well, the formal definition of continuity has a similar appearance. It attaches parameters which measure the kind of rate of convergence of the function, how fast it's settling down to its limiting behavior. Okay? So in the last few minutes here, I'll just draw a picture for it. And the picture is in the notes on page 30. Well, there's one version of it on page 38. But I'll try and draw. Well, even just drawing it again and assembling the various parts of it. So here's a point A in the domain. and you come across to here, here's the value of the function at A. Now the formal definition of continuity, it's an epsilon type of definition. And again, the epsilon parameter measures is a radius around the limiting value. And the way the definition works is if we say how can we ensure that the function values are at least this close to f of a. We consider epsilon to be some small radius around the values, around the limiting value f of a. So this is the closeness of the function values to f of a. And then we ask, well, where in the domain is that closeness achieved? So we introduce a second parameter called delta. Delta is a radius, but in the domain of the function. So delta is a radius around the limiting argument, a. And the definition of continuity says that no matter what value of, I hope I've drawn it right so that it does work, I think I have. No matter what value of epsilon you choose, no matter what positive radius you choose, there will always exist a delta such that for every value of x within a distance delta of the limiting argument a, for every value of x in here, the corresponding f of x value is within the interval of radius epsilon here. Okay. So it has a symbolic predicate calculus type of formal definition. So this is this string I'm about to write out here is the formal definition of continuity for f being continuous at the point x equals a in its domain, means for every positive value of epsilon, so no matter how large or small our radius around the limiting value f of a is, there must exist a corresponding radius which surrounds the limiting argument a, and the property that these two parameters have is that these are parameters governing this implication here, that if x minus a is less than delta, x minus a being less than delta, that means the x is inside this interval here around a. The distance from x to a, or the difference between x and a, is less than delta. That means your x is located somewhere in here, but this implies that f of x minus f of a, that absolute value is less than epsilon. This statement here, absolute value of f of x minus f of a being less than epsilon, that's saying that the f of x value is somewhere within this interval of radius epsilon around f of a. Okay. Now, just as for the definition of convergence for sequences, you have to take account of the nature of these quantifiers. It isn't just saying, well, you can find one little radius around f of a, and you can find a corresponding radius here, and they fit together, therefore it's continuous. No, it's saying for every value of epsilon. So in particular, or the crucial factor is, as epsilon gets smaller and smaller and smaller, can you always find a corresponding delta here, and the delta will be getting smaller and smaller. Can you always find one so that the whole interval around a of radius delta gets mapped inside the interval of radius epsilon around f of a? If you can, then the function is termed continuous. And it's this formal definition which will allow us to prove theorems 4.3 and 4.4. And I'll prove the first part of it. I'll prove the linearity part next week for you. Okay, we'll finish there. Do have a look at the end of chapter